Now we'll look at an example of a wire with variable density. So suppose a wire goes along x from 1 to 4. Its density at a point x is x squared grams per centimeter. What's the mass of this wire? Well, the shape of the wire is the same as before, the segment from x equals 1 to 4. But the density is different at each point. At this end, the density is 1. At the far end, the density is 16. We can schematically draw this by drawing a thicker line. It doesn't necessarily mean that the wire is actually thicker. It might be the same size wire, just more dense. But for drawing purposes, let's draw it as a bigger wire. So something like this. And again, it might be a situation where the wire is the same size, but they just used different metals along the way. And so it's denser at one end. But for the drawing, just to make it visible, you can sort of imagine that it's a bigger wire, and that's what makes it denser. What's the mass of this wire? At the low end, it's density 1 times 3 centimeters, or it's density 16 times 3 centimeters. So we know that our mass is between 3 and 48. Can we try to narrow it down a bit more? What if we break this wire into 3 pieces and figure the mass of each piece and add them up? So a piece from 1 to 2, a piece from 2 to 3, a piece from 3 to 4, and the densities are x squared, so 1, 4, 9, and 16. That means that this first piece, being 1 centimeter long, has density about 1. So density 1 times 1 centimeter. This next piece has density about 4 times 1 centimeter. And then the third piece has density 9 for 1 centimeter. 1 times 1, 4 times 1, 9 times 1, those add up to 14 grams. Or, this first piece maybe doesn't have density 1, maybe the density goes from 1 to 4, and most of the points are in between, so maybe we should look at the high end. At the high end, it has density up to 4 for 1 centimeter. This next piece has density up to 9 for 1 centimeter. The last piece has density up to 16 for 1 centimeter. Those add up to 29 grams. And that means that the mass is between 14 and 29. So from 3 to 48, we've narrowed it down, 14 to 29. It's still a scope of 15 grams in our window, but that's better than the 45 that we had before. So we've narrowed it down a good bit. We could keep going. This first piece of wire, parts of it have density close to 1, parts of it have density close to 4. Why should we call it all 1 or all 4? Why don't we cut it in 2? And this part has density close to 1, and the last part has density close to 4. Why don't we cut it in 2? So cut that wire into two and cut the next wire into two, and cut the next wire into two. So X is going 1 to 1.5 to 2 to 2.5 to 3 to 3.5 up to 4. And the densities are going from 1.5 squared is 2.25. 2.5 squared is 6.25. 3.5 squared is 12.25. So the mass is approximately, well, the density of this first piece is about 1, and it's 0.5 long. Then 2.25 times 0.5 long. Then 4 times 0.5 long. The next piece has density about 6.25, and it's 0.5 long. Our second to last piece has density about 9, and it's 0.5 long. And then 12.25, and it's about 0.5 long. Again, in every segment, I took the density on the low end. Maybe that's too low. Some of these points have higher density, so maybe I should go on the high end. 2.25 times 0.5. The next segment has density up to 4. 4 times 0.5. And, well, you get the idea. We're going to have 6.25, 0.5, 9 times 0.5. One of these I wrote a plus on the first line, but I meant times. 12.25 times 0.5, or 16 times 0.5. I should say I have not run these numbers, so I leave the arithmetic to you if you're interested, but you get the idea. We could subdivide, and there's still some lower and upper estimation. We haven't yet determined the mass, but we're getting more accurate, right? At the beginning, we thought the density was 1 or 16, but points in the middle aren't very close to either of those. Now, these segments are short enough that points in the middle, the density is not that far off from the end points. So we're getting more accurate here. So if we keep going to shorter segments, we'll get more accuracy, more accurate estimates of the mass. Okay, do you see where this is going? These are Riemann sums. We're just taking a summation of however many pieces there are. We started with just one piece, and then we went to 3, and then 6. So however many pieces, and then we're adding them up. And for each piece, we're adding up the mass of that piece, or an estimate for the mass of that piece, which is the density of a point in that piece times the length of that piece. Delta X is the length of the piece. So this is where we closed our previous video. If we had a piece of wire that we know its length and its density, this would be the mass of that piece of wire. And, well, we have estimates for each piece, and we can add them up to get an estimate for the total mass. if we kept going forever to a limit, then two things would happen. Our estimates would give us perfect accuracy. We would get the exact answer. And the other thing that would happen is that these Riemann sums would approach an integral. All right, let's put it all together and answer the question we started with. In this example, the mass is given by the value of the integral, x from 1 to 4. Our density was given as x squared, and we're integrating it dx. Well, that's 1/3 x cubed from 1 to 4. And if you work out the arithmetic, you get 21 grams. And that's the mass of that wire. And these integrals allow us to handle wires with variable density. Next, we're going to look and see what happens when there isn't just an x. The wire doesn't just go along an x coordinate. What happens if it curves? That's what we'll look at next.